Okay, so this session is an update on the SoftRoCE project. We'll start with an introduction, then go over the development status, and conclude with some configuration examples of how to operate SoftRoCE. So SoftRoCE is a complete software implementation of the IBTA RoCE v2 specification. I encounter sometimes misconception by newcomers that think SoftRoCE is an emulation over TCP, so it's not. Just a short recap, the RoCE v2 specification runs the InfiniBand transport protocol over Ethernet, and the way it does it is instead of running over the InfiniBand routing and link layers, as in the InfiniBand case, RoCE uses UDP encapsulation to carry the InfiniBand transport. In terms of the frame format, we have the MAC header followed by AP, then a UDP encapsulation layer, and finally, the base transport headers, one or more depending on the RDMA operation, the RDMA payload, and the invariant CRC, which covers all the stuff that doesn't change end to end. And finally, we have the Ethernet FCS terminating the frame, and that replaces the InfiniBand variant CRC. The use cases for SoftRoCE are, first of all, ease of development. So you can develop RDMA software on your laptop. It can also be very efficient for testing. You can run a test suite be on a cloud using VMs. And finally, you can have deployments like asymmetric deployments where you have thin clients that use SoftRoCE and operate against a server that maybe uses hardware RoCE. So those are the few use cases examples. SoftRoCE is implemented as a standard RDMA provider. It has a kernel module called rdma-core, and it has a user space library called librarxe. This allows supporting both standard applications and kernel ULPs such as ICER. The transport is implemented completely in the kernel, and the main benefit of that is asynchronous progress, just like TCP. So let's say that you're posting a work request of 1 gigabyte worth of data. So the application does other stuff, and of course, we're not transmitting that gigabyte at once, and we're not creating a bunch of SKBs worth of gigabyte data at once. So the kernel progresses the messages, the processing of the work request as acknowledgements come in and SKBs go out. Of course, the actual NIC is not aware that it's running RoCE traffic. It just gets Ethernet packets. So the NIC driver, of course, doubles as it serves standard IP stack traffic in addition to SoftRoCE. Yeah, that's more or less it. Let's go into a little bit more details on the design of the RoCE driver. So the first thing I want to note is how the queues are created. So in RoCE, all the queues, the QP send queues and receive queues, the completion queue, share receive queue, they're all allocated in the kernel and then mapped to user space. What this provides is that the library, the librarxe, when it posts new work requests or when it pulls completions, it doesn't need to use system calls. It can directly add the work request or detect completion queue entries on this shared memory between the kernel and user space. In fact, the only system call that's used is the one that's used for ringing the doorbell when there is new work. Interestingly, when you post-receive work requests, you don't need any system call at all. When a packet comes in, it just checks if there's a work request to use. Another interesting aspect is memory registration. Currently, SoftRoCE pins down memory regions just like a hardware device would, although it's implemented in software. This allows accessing the page frames that comprise this memory region in any context. So, for example, when we receive packets and process stuff in a software interrupt in NAPI, we can scatter data directly to this memory region rather than wait for the actual process to pull the data in. In terms of scheduling context, currently the implementation uses 3 tasklets per queue pair, one for the requester, one for the responder, and one for the completer. When you're sending new work requests, the initial work actually gets done during the context of the system call that does the doorbell. But this requester tasklet will get invoked in cases such as when you get an incoming acknowledgement and then you can progress from that, or when you have enough, or you hit a rate of a limit of the amount of SKBs that are currently queued for transmission, so the SKB destructor will spawn progress and again trigger this tasklet. When traffic is received through the NAPI context, SKBs go in, get classified to the correct queue pair, and according to the fact whether they're requests or completions or responses, sorry, they get queued in different SKB lists and trigger corresponding tasks, either responder or the completer task. And yeah, that's the basic operation. In terms of development, the RoCE driver was initially developed by SystemFabricWorks a few years back and was presented in OFA. However, work was not completed back then, and kernel submission wasn't completed. 2 years ago, we restarted the project as an open source project with contributions from SystemFabricWorks, IBM, and Mellanox. And finally, last year, the RoCE driver was accepted upstream. So it's now available from kernel 4.8, and the user space part is part of the rdma-core library. Since the submission, there has been a lot of active work on the RoCE driver, mainly in stabilizing it. I just put here a few examples of the issues that were handled. So we had a few logical issues that were fixed, such as handling erroneous wikis or supporting retransmissions of 0-byte operations. There were a few memory leaks that were handled, such as bad reference counting on the sockets that we create to receive traffic. And in some airflows, SKBs weren't reference counted correctly. And there were a few subtle races that under pressure showed up. Like when we update the QP state, when we send out an SKB, there were cases sometimes that incoming acknowledgements caused corruption, and all these were fixed. So the state of affairs is that right now RoCE is pretty stable, and the next challenge is starting to work on performance. The performance right now is not great. It's around several gigabytes per flow, but there are a few tricks up the sleeve that I hope that we can get that to match at least UDP performance, if not TCP. So let's have a quick review of the status of the RoCE driver. So feature-wise, it supports UDRC and UC transports. It supports shared receive queue. It supports atomics, multicast, fast registration, and local and remote invalidate. It was tested both on bare metal NICs and V virtual functions. In terms of testing, we run the standard regression test that we do for hardware. We run it on SoftRoCE, so it passes 100% all the low-level verbs testing, rdma-core testing, perf tests, and also ICER initiator and targets. Other than testing RoCE, two nodes that run RoCE, we also tested interoperability with hardware implementations, so it was validated against ConnectX 3 and ConnectX 4 RoCE v2. So in terms of availability, so it's upstream in upstream kernel, and what's left is the distributions. So I know it's going to be planned to be included in Red Hat CentOS 7.4 and Ubuntu 17.10. In terms of Mellanox OFID, we have included support for RoCE starting from this recent release that's coming up of MOFID 4.0. It's kernel 4.9 based, so and it has also backports for 4.8. So it means that you can install it on Ubuntu 16.10, and it also has 4 ports for kernel 4.10. So you will be able to install it also on Ubuntu 17.10, 17.04. Let's a little bit to get the feeling of how you configure it and how you use it. So once you install the software, you manage RoCE through the RoCE config tool. The basic tasks are starting and stopping the RoCE driver stack, adding and removing interfaces, and looking at status. Any configuration that you do is persisted in a configuration file. So if you stop the stack and then start it again, all the RoCE devices that you configured prior to stopping the stack will show up again, and it can also be persisted across reboots. The way that you add devices is that you specify a physical netdev and associate it with an RoCE instance. There's a limitation that you can have only a single RoCE instance associated with each net device. I don't think it makes sense to have more. So once you do that association, you can later reference it either by the netdev name or by the RoCE instance. For example, let's say that I'm starting with an empty system and I'm doing RoCE config. So I see here that I don't have currently any RoCE devices, but I have 3 NICs in the system. I have an IGB and a ConnectX 5 NIC that are currently have their link up. And what I could do now, I can use the add command by just specifying the net device to add an RoCE instance and associate with that net device. So if I now run the status command, I now see that I have an RoCE device created on this ConnectX 5 NIC, and this instance is associated a name RoCE 0. RoCE leverages the automatic addressing that's currently handled in the InfiniBand core. So just like any other RoCE device, it gets its addresses assigned automatically. So if we look at this ConnectX 5 NIC, we see that it has this IP address, this 11.something. And if we do now IPv-dev-info, we can see that looking at the GIDs, we have the same IPv4 address showed up as GID1. Of course, this is the link local, the IPv4 mapped format that encapsulates this address. The first GID is the IPv6 link local address that's also added by the automatic addressing code. So once you have an IP address, maybe that's one other thing that I'd like to say. RoCE doesn't have an independent management framework. It relies on Ethernet management, and that's in contrast to, for InfiniBand, where, for example, you have the SM, you have SA queries. Here, you don't need them. IP addresses are just taken from the matching net devices, and instead of path queries, we have IP routing and ARP. Once an RxC device is configured, you just use it like any other RoCE v2 device. In this example, I'm running IBV RC ping pong. I can put the name of the device and run the standard ping pong test. And again, since it's a software implementation, all the packets are running through the net device as usual. You can just use standard capture tools and use Wireshark to validate the traffic. So in this case, I can see here this .145 station sending a ping. So we have this send only here. And then we have the peer acknowledging that, that send. And then we have another send only, which is the pong. And the original station, again, acknowledges that. So you just see all the protocol packets flowing. And in terms of the packet itself, so we have the Ethernet frame, and then the IP packet, and then we have the UDP encapsulation, finally, the InfiniBand transport header. All of this can be observed in Wireshark. In terms of future work, feature-wise, probably the main feature that's missing right now is memory windows. In terms of the base feature set of an RDMA device. After that, we think of looking at demand paging, SRQ resizing, and maybe XRC. Another direction to work is on congestion control. We have a session on this later on in the workshop, but the idea is that congestion control can add additional benefits, especially in the data center setting for RoCE, like fairness between flows and the ability to operate with lossy networks. Finally, container support. The current kernel does not support network namespaces for RoCE, and we do plan to add that, and once it will be added, it should work transparently also for SoftRoCE. So you can, for example, allocate some, I don't know, VTH device or Mac VLAN device, and you should be able to assign that to a separate network namespace and have a SoftRoCE instance operating on top of that. The main piece of work that we want to do is concerning performance. So as I said, the RxC is stable, but the performance is not there yet. So I've listed here a few ideas that we think are going to improve performance considerably. The first is zero copy for transmits. So since we have the memory regions pinned, the code right now, when it sends packets, it creates SKBs and copies out the data. And there's no real reason to do that. Instead of that, we can directly point to the fragments with zero copy. This would apply to sends, to RDMA writes, and also when you're sending read responses. So basically, whenever we have large data, MTU-sized data, we should be able to do zero copy. One interesting aspect for that is when you're sending UD. Right now, we trigger completions directly when the SKB is queued, but once we will use zero copy, we would need to generate the completion when it was actually sent out, basically when the SKB destructor is called. One note though, although we can do zero copy sends, we still need to go over all the data for CRC calculation. So if you recall the frame format that we started with, we have this CRC field here. which is part of the InfiniBand transport standard. And we're using, the standard uses this CRC and not the UDP checksum, which is a very basic ones complement checksum. And there are very few NICs that can calculate the CRC automatically. So essentially, right now we fall back to software to calculate the CRC to get this standard packet going out. On the receive side, we can't do zero copy because we need to first inspect the packet and then scatter it to the correct memory region. But we can do it more efficiently than it is done today. We think that we can remove completely the requeuing of packets and then handling them from a separate tasklet context. Basically, again, since the memory region is pinned, we can scatter the payload directly from the NAPI context. Another thing that we think that is worth checking is the ability to do the checksum calculations during the scattering of the data, just like it's done right now in system calls for TCP and UDP side. And then there are a few, there's a bunch of other optimizations that maybe each and one of them is a small, but if we apply all of them, we hope that we can boost up the performance. So right now, as I said, we have 3 tasklets per queue pair, and we can probably get rid of those and use something more efficient, like a tasklet per core, and then just queue all the queue pairs that need to be progressed on those shared tasklets. In terms of transmission, right now SKBs are sent one by one. One optimization that can be done is actually send an SKB list. So when the NIC gets the SKBs, it'll have the transmit more bit set, and it results in more efficient sending because the NIC now can queue the descriptors for these packets, but do the actual NIC level doorbell only once per batch. Another optimization is that currently the RoCE driver calls a route lookup for every packet. So although there's a cache, it's still costly. One thing we can do, just like TCP, is cache the route, cache the destination entry, and eliminate that lookup for every packet. In terms of the CRC calculation, the current code uses standard instructions to do the CRC calculation. What we can do is use a crypto driver. For example, the CRC32 PCI mol for x86. I think it's basically what's been pushed for ASNI. So basically on any x86 server, we can call this driver and do the CRC calculation more rapidly than the current implementation. Finally, there's a degree of freedom when you're sending RoCE v2. In the UDP encapsulation header, the destination port is well known. It's the YANA well-known RoCE v2 port, but you have freedom to choose the source port. Currently, that value is fixed, and if we change it according to the entropy of a connection, so for example, per QP will have a unique source port number, but different QPs can have different source port numbers. And the benefit of that is twofold. First of all, we'll be able to use multiple transmission queues on the NICs. The standard select queue method does a hash, and it takes into account the UDP source port in the hash. So that's one benefit. And the other benefit is in the network, where switches can do ECMP on different reliable connected flows. And that's it.
Have you tested any other upper layers than ICER? That's the only one I saw that was in kernel storage oriented.
I'm trying to think what would be valid for that. So obviously, SRP and IP over IP wouldn't. Maybe NFS RDMA could be a good candidate as well. Until now, we have done only ISR testing in terms of ULPs.
Okay. Obviously, they'll be RC oriented, and they will have, a fairly small set of requirements, right? Send, receive, RDMA read, RDMA write.
Yeah. There's no reason, for example, why the NVMe over FABRICS driver wouldn't run over SoftRoCE as well.
Yeah. They might be, A, relatively easy, and B, relatively important, and they will stress it very hard, right? You can generate a lot of load. Strongly recommend you try that.
Yeah.
Okay.
It's actually, again, if I go back to the use cases, so for testing purposes, this could be a really good option. Again, performance, we still have a way to go, so I'm not sure that makes a lot of sense to deploy such things right now.
Well, yeah, I mean, it's a work in progress. That's totally understood. But, I mean, it's the upper layers that drive the demand for this thing, right? It's not just because it's there that it's interesting. It's got to actually work. So you might as well embrace upper layers. Okay.
Yeah, will do.
Hi. I was wondering if you consider using this software implementation as a way to test the hardware. For example, by injecting errors, stuff like that.
I think it's a very good idea. Whenever you have the control, I mean, we have special tools that do the same thing, but I think that now that SoftRoCE is in mainstream kernel, I think it's going to be very easy to do frameworks that do that kind of things. Yeah, definitely.
Okay, another question. I think you said that SoftRoCE doesn't support RDMA-CM?
No, it does. It's
okay.
I just said that in terms of testing, we validated also rdma-CM.
Okay, thank you.
Yeah.
One question, do you support PFC in it, like with multicores in the NIC driver or anything?
Do we support PFC?
Yeah.
Yeah, so the current implementation of SoftRoCE doesn't implement congestion control yet, so it requires a lossless network to operate well. The PFC itself is not the attribute of SoftRoCE, it's an attribute of the underlying NIC. So what you would do, you would enable PFC on your underlying NIC and...
Yeah, but you need some kind of support from the NIC, right? Like multicores or something, so you'll be able to transmit according to the priority. I mean, if you just transmit on the L2 queue, it will be on priority 0.
Let me put it this way. So losslessness and quality of service are separate things. Theoretically, you can use a single queue, but then you would have implications of quality of service. But I think today all NICs are multi-queue, and especially those support PFC, I think.
Okay. No, I mean, if you just have one queue, you can use legacy pause as well, right? There's no...
Sorry, if I have...
You can use legacy pause and not PFC if you have just one queue.
Yeah, you can.
Okay.
You definitely can.
What about ECN?
ECN is exactly the work about congestion control that I'm talking about. So
that's
ECN,
future work?
It's future work. ECN is, for RoCE v2, is standardized by the IBTA, and it's future work.
Okay. Thanks.